Earlier we said flat fading occurs when we have an ellipse and the transmitter and receiver, they are present at the two focal points of ellipse, and the reflectors and scatterers, they lie on the ellipse. So what we have is we have n number of paths going from the transmitter and reflector. So as a result of this geometry, what we say is the propagation delay of all the paths is linearly equal. That means all the paths, they arrive at the receiver at almost same time. So then we can say tau 1 is equal to tau 2 is equal to tau n is equal to tau hat. So this was our first assumption for the flat fading. And second assumption was phi and the phase, it is uniformly distributed in 0 to 2 pi. And we also said that even though this tau n's, they are separable, but phi and t's, they are not separable, because phi and t was a function of fc into tau n, and even a small change in tau n of order of 1 nanosecond gives a phase rotation of 2 pi. So this is when we have flat fading. So even though in flat fading we saw that the response is flat in a band of frequency, but it is time varying. It is varying with time. So we have a property time variant. And also we have seen that this hi of t is given by summation n cn cos of theta n of t, where n goes from 1 to n. This phi n is uniformly distributed and this n is very large, and thus we can invoke central limit theorem to obtain the distribution of hi and t. And we said that this hi of t follows Gaussian distribution. Similarly, hq of t also follows Gaussian distribution. So as a result of this expression where ht is equal to hit plus jhq of t, we say this h of t is random in nature and also follows Gaussian distribution. So as a result, we have a randomness in the channel. So then we have also seen that when s tilde of t, first it is getting some delay, s tilde of t minus tau 1, then it is getting multiplied by the coefficient h1 of t, and similarly we have other paths with some delay t minus tau n, and then at the last the all paths are added and we get r tilde of t. So this received signal can be interpreted as the outcome of the linear filter. So as a result, the channel is randomly because h is random in nature, time variant because the response is flat in band but is time varying, and then we have linear filter as if the r tilde t is as we can say r tilde t to be an outcome of the linear filter, and the coefficient of this channel is represented by h of t. The next also this since we are passing S tilde of t to be 1, the magnitude of S tilde of t, this is the band of frequencies, and the magnitude of S tilde t is varying with time. And to capture this amplitude, we said alpha is equal to h of t, the mod of h of t, where this envelope can be Rayleigh distributed or Rayleigh distributed. So different from Rayleigh distributed, Rayleigh distribution, they have a strong line of sight link. That means between the transmitter and the receiver, we have a strong line of sight connection. Or if there is no strong line of sight connection, we can also say that it has strong specular component because of strong reflector present. And the other parts, they have significant less signal strength compared to this component. And if we see the distribution of this Rayleigh fading, we can see here that this K is the rise factor. And when this K is equal to 0, this Rayleigh is transformed to the Rayleigh fading. So that means the distribution of Rayleigh can be seen equivalent to the Rayleigh distribution. And as this K is increasing, the distribution becomes narrower. And when K is equal to infinity, we can say as if this is the scenario where there is no fading. Or we say it is AWGN channel, or our channel is experiencing idle conditions.